Hi, hello everybody. Welcome back to Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and for this, Chapter 6, Lesson 5, we're going to be talking about trim changes with weight additions and weight removals. Now, before you get too far into this video, I would highly suggest that if you're not extremely confident in yourself when it comes to those trimming arms with weight shifts, I suggest you go back into that video, work a couple example problems that you make on your own, and try and make sure that you are very confident in that before you start getting onto this. There really isn't much of a difference between weight additions and removals and weight shifts. However, I'm not going to go too far into the weeds with that trimming arm, trimming moment, and everything that I covered in the last video. I'm just going to introduce a new concept called parallel rise and parallel sinkage. So let's start off with this little statement here. With weight additions and removals, the only difference from weight shift is parallel rise, parallel sinkage. Now, what is parallel rise and parallel sinkage? So the ship, I talked about that pivot point, the LCF. Now, the LCF also has another kind of alternate reason for being. If we add weight directly onto the LCF, there's no additional trimming moment that's going to go onto the ship. So by just weight addition right onto the LCF, the entire ship is going to sink parallel. So if we put, say, 100 long tons onto a ship and it causes it to sink 3 inches, the forward and the aft are going to sink 3 inches. Same thing with parallel rise. Parallel rise means that forward and aft both rise parallel. So if we do the same thing, remove 100 long tons, so we get the ship rising 3 inches, the forward and the aft are going to rise 3 inches. So the drafts are going to change. With parallel sinkage, we know that the ship is going down. Our arrows are always pointing down, giving down positive. That means that parallel sinkage, we're going to consider positive. Parallel rise coming up, up being negative, we're going to consider parallel rise to be negative. All right, so let's go through some generic examples of a weight addition and a weight removal and see how everything behaves with parallel rise, parallel sinkage, and then trimming. So let's start off with a weight addition. So right here in this diagram, we have a ship just sitting here at a condition 1. We have an LCF right here. We have this weight and we want to add it to the ship. Now, if you pretended that you just added the weight directly where you were going to finish moving the weight, there'd be a lot of very, very involved calculus differential equations in order to actually solve that. We can use the law of superposition, however, and make this infinitely times more easy. So if we add the weight directly to the LCF, that's going to give us parallel sinkage. Then we shift that weight, nothing different from what we learned in the last video, to its final location. Then we're going to account for the trimming. Then we just add, through superposition, just add the effects of the weight addition, parallel sinkage, and the trimming to forward and aft, and we're going to get our complete total change in drafts, forward and aft. So let's go here. We have a weight addition. We're going to put it directly on the LCF. By putting it on the LCF, it means that there's no trimming moment there. So we're going to have parallel sinkage because we're increasing our displacement, and we learned in several chapters ago, we learned that increasing displacement makes the ship sit a little bit lower in the water. So add it to the LCF, we get right here. So here, with this dotted line, was our state 1 from here. Now we have state 2, this line. We've completely parallel sank, so forward and aft drafts both sank an equal amount. Now we have that weight at the LCF, but we don't want to finish it at the LCF. We want to finish it somewhere forward. So we just shift that weight to some point forward. Now, all we do is what we've seen in that previous video with change in trim, delta D aft, delta D forward, nothing out of the ordinary with that. So now you see, we were at 1, went to 2, now we're at 3. With this this forward trimming moment, we know that our bow is going to sink deeper. So that's going to be positive. We know that parallel sinkage is going down. That's positive. So we have a positive with sinkage and then positive with the delta D forward, which means that we have plus and plus. And you see here, you have the effect of parallel sinkage and then the forward trimming moment. Now aft, however, it's going to be positive because of the parallel sinkage, but it's going to pop up a little bit due to the trimming. So we're going to have to add the parallel sinkage and then subtract the trimming moment, or sorry, the effects of the trimming moment. So now we have to do a little bit more housekeeping on all of our values and make sure that we're doing things correctly and in order. Now for a weight removal, it's pretty much the same thing, but a little bit different. So we start with this condition here. We've got a ship at, this would be 1. Condition 1, we have a weight here on the forecastle somewhere. Now, to get rid of it, we first have to get that weight to the LCF. So we have to shift that weight. So we shift it, moving over here, we get this trimming moment. We have our, because it's an aft trimming moment, now we have the aft going deeper, and we have the bow coming up. We have the bow getting shallower. Now we have this weight on our LCF, but that's not its final location. Its final location is completely off the ship. So now we just have to spring it off. So now we have the W up here, just out in the air somewhere, maybe a helicopter took it away. So because we lost weight directly at the LCF, that means we have parallel rise. So now we have the ship that went from, see, this was state 1, this was 2. So now we had 1, 2, and 3. Now, look at this, we know that down is positive and up is negative. Started here, we have a negative going from 1 to 2. That was our trimming moment factor. Then we have another negative influence from 2 to 3. That's from our parallel rise. If we look at the aft, however, we had the original, then we actually went down, so that's a positive. Then we subtract for the parallel rise. So you'll see here, in this instance here and this instance here, the counteracting effects don't necessarily cross what the original state was. However, it is very possible that you could have a final state. So we had the original right here with 1, then it sank here. It is very possible, due to the LCF and where different things are, how much weight you're moving, what that trimming arm is. It's very possible if you put weight on the aft end to get something like this. So if we put weight here, in this situation, our forward, our bow, actually became more shallow than it ever was originally. So it sank with the parallel sinkage, and then because of that arm, that trimming arm, it popped up all the way. So now you see this, to bring weight addition and weight removal into the realm of weight shifts, our trimming arm is going to be the distance from the LCF to the final resting place of the weight. The weight's given to us, so we know trimming arm and the weight, therefore we know the trimming moment, we know the change in trim, and we know everything else. How do we find this parallel rise or parallel sinkage? Well, right here, PR is parallel rise. This line does not mean division, it just means or. So parallel rise or parallel sinkage. You can't have a ship that does both simultaneously due to just one weight addition or removal. So parallel rise or parallel sinkage equals the weight divided by TPI. TPI is tons per inch immersion. TPI equals tons per inch immersion. That tells us if we add so many amount of tons, it's going to cause the ship to sink or rise 1 inch. So if our TPI, typically it'll be in, I said tons per inch. So let's say it's 64 long tons per inch. And we added a weight that was 32. We had 32 divided by 64. That would give us 0.5 inches, because long tons divided by long tons per inch is going to give us inches. So in this quick little example, if we added 32 long tons to a vessel that has a tons per inch immersion of 64, we would only have 0.5 inches of parallel sinkage. And if we removed that weight, so if we removed 32, we would have 0.5 inches rise, parallel between bow and stern. All right, now for the example problem. Just like I did in the last video, I'm going to do this one with you in real time so you can see my thought process on how to solve these problems. Now let's take a look at the prompt. We have a ship, LBP equals 300 feet, and we're going to fill a fuel tank, 4-tech 240 tech 0-tech Foxtrot, with diesel fuel to 95%. Length is 20 feet, width is 30 feet, H is 10 feet. All right, that's not the most ideal way to get that information across, but I think I can work with that. Frames are 1 foot spaced. All right, nice. LCF is 9 feet aft of the middle perpendicular. TPI, tons per inch immersion, that we learned earlier, is 20 long tons per inch. That's going to give me my parallel rise and parallel sinkage once I find the amount of weight that I have added. MT1, moment to trim 1 inch, that's going to be 2,400 foot long tons per inch. So I'm going to be dealing with a trimming problem here. My draft aft equals my draft forward, which equals 10 feet, and my drag equals 0. So my ship is sitting right on the horizontal with 10 feet aft and 10 feet forward. Great. I think this is all that I need in order to get this problem done. So now let's let's label everything that we have on a diagram here. So we originally have a ship here, and then we're adding all this fuel into this tank. So let's start working here. I know my forward perpendicular is going to be at 0, so let's say 0. Now I have a LBP of 300 feet. So my aft perpendicular is going to be 300 feet. My middle perpendicular is going to be 150. And then my LCF I know is 9. So it's 9 feet aft of the middle perpendicular, which means I have to increase my frame numbers. So this LCF is 159. Now I also have a little bit more information that's going to tell me the center of gravity of the fluid or the diesel fuel that I just added. So we all know about these tach numbers. 4 tells you the deck. This second number tells you the frame of the forwardmost bulkhead. This tells you relation to centerline, and that just tells you the assignment of, or the type of compartment it is. So if we use this 240, we know that that is the forwardmost bulkhead. So looking at everything here, I know that this here is my forwardmost bulkhead, and that's going to be 240. I also know the length of the compartment. The length of the compartment is 20 feet. If my frames are 1 foot spaced, that just means that my aft bulkhead in that compartment is 20 feet aft, or 20 frames. So if I start at 240, that means the aft bulkhead is at 260. Now we know the center of gravity is going to be right in the middle of those two bulkheads, assuming that it's a perfectly rectangular compartment, and based off of what we've been given with a length, width, and a height, we can assume so. So our center of gravity is going to be right between 240 and 260. That's going to be 250. Excellent. So we know this is a weight addition, so I already have my writing arm. My trimming arm. I have a frame here, 250, for my center of gravity. I have a frame for my LCF, so all I got to do is subtract the two, and that's going to tell me exactly what I need. But let's kind of take a look at what else we need. So we have LBP, we've got all that. We filled this with diesel fuel 95%. So let's start working on weight. How much weight did we add? We know length, width, 95% of height. So take our calculators here. We got 20 times 30 times 10 times 0.95, which is going to be 9.5. Then we're going to divide that by the specific gravity of diesel fuel, which is going to be 43. And we're going to get 132.56. So weight equals 132.56 long tons. Great, that's something that I really need in order to do anything with moments. It's a force times a distance. I got a couple of distances, I need that force. So I got that force right here. So great. Now, let's do parallel sinkage first. Like I said, step 1 is going to be get that weight to the LCF. Then step 2 is going to be get that weight to the final destination. If we have a weight addition, let's say the weight is up here, we're going to add it to the LCF to get our parallel sinkage, then we're going to shift it. So we're going to do the easy part first, then we're going to do the hard part. To do parallel sinkage, we know that parallel sinkage equals my weight divided by TPI, my tons per inch immersion. So how many tons will give me 1 inch of immersion? That is right up here, 20. So I take my W, which is 132.56. So 132.56. And I'm going to divide it by my TPI. That's going to be 20. Divided by 20. It's going to be 6 point something. Yeah, 6.63 inches. Now I'm going to keep that like that because I know that parallel sinkage affects both my forward and my aft drafts. So I'm just going to box this in red and hold that off to the side for now. So now I have my original condition. Now I've added my weight. So I was here. Now, I'm sorry, let's erase that real quick. I went from here. Now I'm here. I've done parallel sinkage. So I've gone from state 1 to state 2. Now I have a ship that's sinking, or that's not sinking, that has sunk 6.63 inches. And remember, that's inches, not feet. So it's 6.63 inches. But that weight is at the LCF right now. I need to shift that weight over to its final location in order to find all my trimming moments, the changes in draft, and then finally add everything together and see what I get. So I sank. So my LCF is there. LCF is here. Now I got to do one more. I know it's at the LCF. Now I have to shift aft. Shifting aft means that the aft end, the stern, is going to sink. Forward is going to pop up. So I was originally at 1. Then I went to 2. If that was my LCF. Now, shifting aft, sinks down. My final location, my final condition of the ship is going to look something like this at 3. Which means if down is positive, remember, with trim, down is going to be positive because it just matches up with our drafts and how they work. My draft aft is going to be my parallel sinkage plus my delta D aft. My delta D forward, my draft forward is going to be my parallel sinkage minus my delta D forward. So now let's work with this. So step 1 is to find out exactly how everything's going to behave. Already done that right here. Next, we got to get our trimming arm. We know that we add the weight to the LCF, then we shift it. So we're shifting it from 159 all the way to 250. So that's going to be 91 feet. Yeah. Yep, 91 feet. So we do TA equals 91 feet. Now we do our trimming moment. How do we find our trimming moment? We just take our TA times the weight, force times distance. So, or distance times force in that regard. So we have our weight, 132.56. So 132.56. Then we're going to multiply it by this 91. And we get 12,063. So TM equals 12,063 foot long tons. The calculator really reads 12062.96. I'm just going to round that up because 0.04 is minuscule compared to the actual number itself. So now we have trimming moment is 12,063 foot long tons. Great. What's the next step? Do you remember? We got to go to our MT1, our moment to trim 1 inch, find out how many long tons it takes to trim 1 inch, compare it to how many long tons we have, and see how it works. So MT1, my CT, change in trim, equals trimming moment divided by moment to trim 1 inch. So I take my 12,063. I'm going to divide it by 2,400. So I get 5.03. All right, so I had parallel sinkage of 6.63. Then I have change in trim of 5.03 inches. But this isn't going to directly affect my drafts. I have to kind of distribute that among the forward and the aft. So now we know our ship looks like this. Here, and if our LCF is here, we have to move that up. That's a little off. There we go, not much better. But we had originally here, this is our change in trim. Now we gotta shift it up. This is my delta D forward. And this is my delta D aft. And you see this here is the same as this here. Change in trim equals delta D aft plus delta D forward. Great. Now we just go back to that formula that we had for delta D forward, find out that, then we just subtract that from CT and get delta D aft. Keep everything positive for now, then we go back and assign positive and negative to everything. So we know that the LCF is at frame 159, which is just length between perpendiculars divided by 2 plus LCF, LCF being 9 right here. So now we just do that length, so 159, divided by the overall length between the perpendiculars, which is going to be 300. I'm going to multiply that by my change in trim, which is 5.03 inches. And I'm going to get 2.67. So my delta D forward equals 2.67 inches. Now, subtracting this from my change in trim is going to give me my delta D aft. So 5.03 minus 2.67 equals 2.36. Delta D aft equals 2.36 inches. If I add these together, I get 4, 9 to subtract that, yep, 5.03. So now I have everything going down, sinking 6.63 inches, but then I have the forward part of the ship bumping up 2.67. If I know down is positive, then this has to be negative, which means that aft has to be positive because it goes down with the parallel sinkage. Here we go. Down with the parallel sinkage here. And then it goes an additional bit down. Whereas the forward, it goes down with the parallel sinkage and then it pops up a little bit. So now all we have to do is superimpose these, which just means add them all together and then see how it affects the drafts themselves. So parallel sinkage, 6.63. So forward, let's say right here we get forward, 10 feet, 0 inches. Then on this side, so if this here is forward, we start with 10 foot 0 inches. And then aft, we had 10 foot 0 inches. Now let's start doing parallel sinkage. We're going to add our 6.63 inches to this. So both are going to go from 10.0 to 10 foot 6.63 inches. Because it's parallel sinkage, it happens on both of them. So now the ship is now sitting at 10 foot 6.63 inches. Now I know my forward pops up. I know my aft ducks down a little bit more. So I'm going to start on the aft part because it's a little bit easier. Then I'm going to go forward. So with the aft, I just add 2.36 inches to this. So that's going to be 10 foot, see, 8.3699 inches. So I'm just going to round that out to 10 foot 9. That's going to be my final draft for the aft. Now I just do forward. I have, what is that? Okay, 10 foot, 6.63. Then I subtract 2.67. So 6.63 minus 2.67 equals 3.96. So 10 foot, 3.96. Which we can basically just round that back up to 10 foot 4. So now we have a ship that is sitting. It was originally at 10 foot, both sides. Then now we have 10 foot 9. So we sat down. Then we now have 10 foot 9 over here and 10 foot 4. Yep, 10 foot 4 over here. Let's check with our change in trim and see what happens. We originally had 0 trim and we had 0 drag. Now let's check our change in trim and see if that the total difference in the drafts equals my change in trim. 10 foot 9, 10 foot 4, subtract those together, we get 5 inches. Because the aft is deeper, that is trimmed by the stern. We see here CT 5.03, extremely close to 5 inches. And we know just by the nature, we're shifting that weight to the aft. We know that we're going to have trim by the stern. So this and this are correct. All right, now here's a good exercise for you to do on your own. Take this final condition and now remove that weight, or I'm sorry, remove that fuel out of that tank. So pretend that your ship is steaming and you've been steaming for a couple of days now and you have just burned all that fuel. Now reverse everything, pretend it's a weight removal. Now see if you get your drafts to be where we start out with, 10 feet. See if all that works out. Because I've done a little tiny bit of rounding, you might be a few decimals off. That's okay, because think about it. If we have a change in trim of 5.03 inches, and we're talking inches, not feet. So can you really measure 0.3 inches, especially knowing what you know about draft marks? Draft marks, you know, the water is always splashing on them. It's a little bit difficult to get a very, very exact reading on it. So do you think that 0.03 of an inch really matters? Do you really even think 0.63 inches matters? We only really care about the inches because we have a relatively good resolution of ½ an inch with our eyes. So if you don't get the exact answer, so if you don't get exact 10 feet on both sides, don't worry. If you get, say, like 9 foot 11.7 and then 10 foot 0.3, that's all good. You're getting close, but you're starting to understand the concepts and understand not just the memorization of equations. It's not fun to memorize. It's better to understand how things are related to each other. That way it's a lot easier to run through these problems. Don't just try and memorize, try and understand. And that's what I'm trying to get to you. Now, we've just finished up trim with the weight shifts, weight additions, and removals. We're going to talk a little bit more about trim, talk about the navigational effects of trim, why we want to have trim, why we don't want to have trim in certain situations in later videos. We're going to see it again in future chapters. But until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.